Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Computer Wednesday, we're going to talk about JBODs or just a bunch of disks. So let's dive deep into it. So why do we need just a bunch of disks? Well, reality is that our data needs are growing exponentially. What does that mean? That simply means back in the old days of 2010, we used to have barely around 2 zettabytes of data. That was considered holy damn. Yeah, to 2020 we crossed 64. So yeah, we are not only growing, we are growing exponentially. So fundamentally, we need bonkersly large amount of data storage on cloud level, on household level. We need it. Now, there was one technology that was developed in very early, 1970s, that was classified as redundant array of inexpensive disk. Now, that's the idea. Whenever you talk about RAID, it's an idea, redundant array of inexpensive disks. That's the idea. How do you implement it? That's up to you. We'll discuss that further. And but there is fundamental requirements. Whenever you're talking about large data set, single hard drive will not fit it. Single SSDs will also not fit it. So you have to have certain criteria. Criteria number one, must not fail in case of single point failure. Meaning, if you have 100 hard drives, one hard drive goes and you lose the data on it, yeah, that's a no. That's like no. And there are certain laws, like especially for financial transaction, bank cannot just oops a record. Like they cannot oops it. So trust me, there are many things where you cannot just like oops it. And again, imagine it's a cloud service provider who is like paying, has paying customers, and they're like, hey, I pay you this much money, keep this data for me, and they lost that data. That's not acceptable. So fundamentally, no matter what happens, single drive should not cause a failure of data, failure of the array or data loss. So it must be resistant. That's the whole point of redundant. It should be like, I got this. Another aspect is, once we are talking about something large, you are also realizing that these puppies, like let's say mechanical hard drives, they are not fast, no matter what you are dealing with. Like it does not matter, oh, it's a 2 terabytes slow. No, it's the same speed as 22 terabytes. You are lucky. If you are like ludicrously lucky, you will touch 200 and 250 Mbps. Ludicrously lucky if you are. So the moment you have file overhead and all that stuff, and in fragmented files, yeah, good luck with that. And what about SAS, enterprise hard drive? Yeah, no. Like, no. Like 200, you can count on it. Maybe 150, good, got this. 150 to 200, yeah, it's a good day. On a good day, when you have like, good enough. 250, yeesh. Like on paper, everybody claims that, but yeesh. So you can have an interface as fast as possible, but the outcome would be the same. That mechanical splatter limitation. And again, to solve it, we, like for example, cheap drives like these, they generally come in like 7,000 or 5,000 RPM. And once you go a bit higher up, they go up in 10,000 RPM. And then for enterprise, they go up to 15,000 freaking RPM. So not only the power consumption goes up, it also shortens the lifespan. So you have to understand the read and write speed is always limited. But imagine if you had 100 of them and you had that link speed, it's not gonna work. So not only you have to increase the capacity, which you are doing by adding multiple, you also have to increase the throughput, meaning how quickly you can dump data and extract data out of it. That must go proportional to that. Again, that proportion will be defined by you in the configuration, but it must grow. It cannot be like, oh, I have 1 terabyte of hard drive, that is 250 Mbps. So I have 1 petabyte, still 250 Mbps. That's not acceptable. It must scale up. How much? That's up to you, but it must scale. That's the whole point. It must scale and must handle multiple users or load. Like for example, whenever you are talking about data storage, you have to understand servers are not hard things to do. They are simple computers, but their job becomes hard because they are supposed to handle hundreds of people, thousands of people. Or generally, when you are building this sort of system, you could have a requirement from the high ups where they're like, hey, I want one stack to at least handle 1,000 customer per hour, or maybe higher than that. But some are so high that, especially for financial transaction, few million transaction per minute on a server stack, so to say. So it's a very difficult task, not the task itself, but the amount of task, because you have to deal with so many people. And that's why you need the throughput to go up. If all the throughput is limited by the slowest link, that's not acceptable. There won't be any point. So these are the need. That's why we need just a bunch of disks, like bonkersly large amount of disks, maybe 50 disks, 100 disks, 5,000 disks. So RAID was the first idea, first iteration where we tried to solve this, which we call redundant array of inexpensive disk. Now, be mindful, it's a concept. How you implement it, it's up to you. Generally, whenever you are talking about RAID are implemented on a hardware level. And the name, the idea RAID, this acronym started in University of California in 1987. Now, be mindful, others had used similar sort of protocol, and I'm talking going back to the tape drives or punch card. People have used those sort of system, but there was like, you need certain sort of like, body of that figures things out. Like, you do not want every company making their own interface. You want like PCI Express to be made by one people. You want USB to be managed by USB association, Bluetooth by Bluetooth association. Same way, this basically group of smart people, they've created a ecosystem where everybody's like, okay, that's what we are doing. What are you doing? Oh, we are making redundant data. No, we are doing RAID. So that allowed everybody to agree to it. Basically, user, programmers, developers, manufacturers, everybody could like, okay, we are working on RAID. So that happened in 1987. Now, there are a lot of configuration, bonkersly large amount of it, but core fundamental kind of remains the same. So the core fundamental is RAID 0, that is striping, meaning you you add 2 drives and you increase the capacity. So instead of having one hard drive that is, let's say, 100 gigabyte, you have 2 hard drives that gives you 200 capacity in one folder storage. Okay, boom. Now you can see a problem, like how the hard drive, like what happens if one hard drive fails? Nothing. You lose your data simply because, again, the data was striped. Now, is there a benefit to it? Yes, read and write speed can double. So that is there. Then you have mirroring. Now, mirroring kind of requires a lot of computation, because again, you are repeating the same action on 2 drives, but again, it gives you redundancy. That's the bare minimum you should have. Whereas like, hey, what happens to if one hard drive goes YOLO? Again, second hard drive has all the data. You will not suffer loss of data. So that's there. Then you have RAID 5. Now, RAID 5 this is where you actually start to get into serious things, where you have, let's say, 4 drives, and then you are reading and writing on all of them. And this time, now you start to get into the benefit of having that many disks. You can literally get a much higher read and write speed, simply because, again, so many drives are absorbing in it. If the controller is fast enough, let that be very clear, it's on controller. If the controller is fast enough, it can slice data quickly enough. Let's say each block data is 512 bits of block. So 512 bit data is like going tick, 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 tick. Now, each can easily absorb at 250 Mbps. So if the controller can send that kind of throughput, like 250 multiplied by 4, done. Now you're going to have ludicrously fast speed. And what happens if one hard drive fails? You go to what we classify as degraded state, but you have all the data. So, and which hard drive could fail? This is the neat part. Any hard drive. It does not matter this hard drive, this hard drive, this hard drive, or that hard drive. That's the whole point of redundancy, meaning anyone can go YOLO, but your data will be there. Now, what to do if it goes YOLO? Now, this is where the danger happens. Now, generally, whenever you're talking about these sort of puppies, they have a reliability curve, meaning if they do not fail on the first year, the likelihood of them failing is almost 0. But after 5 years, it goes up again. So you have an array, and you have, let's say, 4 drives, and one drive goes kaput. You're like, okay, let's shut down everything. Let's pull the drive. Let's put a new one in. Let's rebuild the array. Now, that's the most dangerous operation you can do on any RAID system, simply because at that point in time, you have 5, basically, let's say 3 drives that are old, that are reaching that point. Now you are putting a brand new hard drive, and you are trying to write data to it. That's the whole point of it. The moment you try to write data to it, it will go through the whole drive. Especially if it's full. Let's say each drive is almost 80% full. It has to read all of the bits, all of the drives, all 3, all bits. That's brutal. Now you read and write operation on all of them, stressing it out. Like normal user would be stressing it out to 10%. Rebuild operation or scrubbing kind of operation, that will be stressing those puppies to 80% of capacity. Yeah, the likelihood of second hard drive failure is extremely high because of that curve. So a degraded state is not a desirable state. If you detect a degraded state, you must replace it as quickly as possible, because any wait, you are pushing the probability of second drive failure. And the moment second drive fails, you are in data loss territory. And what about these fancy terms, RAID 10 and stuff? Is just the same thing. It's a RAID 1 and a 0. So you have like 2 drives in striped and 2 drives in mirror. Benefit is you get capacity 2x, but your read and write speed goes up exponentially. Assuming, be mindful, many times people say, oh, your read and write speed adds up. It depends on the controller. If controller is sloppy, it's not going to work. Controller needs to do the crunching. So, but again, if you are in a, let's say, enterprise environment, you have multiple users, generally prefer 10, because data loss is very high penalty. You cannot afford to lose data. At that point, it's like, hey, I can risk 2 hard drive. And again, rebuilding this is far easier compared to rebuilding in this scenario, because again, likelihood of 2 hard drive failing at the same time is low. So That's how we deal with this. Like RAID 0, simple striping, you're just adding 2 of them. RAID 1, you're cloning data. RAID 5, you have mathematics involved. Now it requires a lot of crunching power. RAID 10 is the same 1 and 0. So basically 4 drives, 2 of them are backup. And any 2 can fail. Let that be very clear. Any 2 can be fail. You will not lose data. So these are the bare minimums, and then you have far more complex operations. Now, pool capacity increases. That's the whole point. Once you add a few of them, pool capacity increases. So 2 terabytes, add multiple of them. Now you have one folder in a computer or network share that could be like bonkersly large. And throughput. Based on your controller's capability, your throughput could go very fast. How fast? Gigabytes per second. Even though each unit is only limited to 50, you can easily achieve gigabytes per second. So that's there. Now you have to understand this happened long ago. Like 1987 is the formation of the era. So that was long ago. Like that was so long ago that gigahertz was unattained at that point in time. Like we are kind of spoiled that the first computer I even touched was like 3 gigahertz. Back in those days, people were like 500 megahertz. Like I find it shocking that megahertz was like an actual computer term. Like the news processor, 500 megahertz. I'm like, damn, my ESP32 can almost touch it. So, but you have to understand, back then that was the thing. So computers were very weak. So that's what gave the rise to hardware RAID. That's why hardware RAID became a thing, because there was not enough compute power in the processor. Processor was bogged down just by file system. So it was like barely, I cannot do that parity calculation. And be mindful, if parity calculation is not happening fast enough, you can have 10 hard drives. It will just not be fast enough. Throughput will not increase. So you needed that. So what was the solution? The solution was PCI Express card, and they put a whole computer in that. Basically, they put ASICs, application specific integrated circuit. The whole system was designed as a miniature computer whose sole job was, I do parity calculation. And they were very good. That's how we developed the internet. It did work. And again, you can see they had RAM, they had batteries. Like, why? Well, it's a computer, and the problem was that if data was dumped into the RAM and power went out, there was nowhere for the data to go. So, and be mindful, this is like, 90s. So there was no flash storage. So the idea was very simple: have a battery and it should last at least 24 hours. So the idea was, in 24 hours, you should figure out what to do, either to restart and basically figure out a power supply, or have this transplanted in something else. Like you have to do something. And that 24 hours was your buffer period. Do something. It had to be done. That was the only option. However, while everybody developed their own solution, it created a paradox. It created fragmentation. Hard drive, you do not care. You can buy from Seagate, you can buy from Western Digital, you can buy from Dell, you can buy from whoever. Who cares? Nobody cares. But when it came to RAID cards, yeah, it became vendor locked. Meaning, if you are buying Dell, you're buying Dell RAID technology. You cannot just, okay, let's say the Dell card fried itself and you went to Dell. It's like, bro, I want a replacement of this. They're like, okay, it's going to be $5,000. You're like, no, thank you. You go to LSI. LSI is like, bro, I got you $3,000. You're like, hey, cool. You put it, all the data is gone. Why? Proprietary method of pirating the data. Like it required like data forensic in order to recover system if RAID card failed, and if you do not find the exact same brand of RAID card. So that was not acceptable. But again, that was the only way to getting things done in 1970s, 80s, and 90s. Like by 1990, early 2000, people were starting to get pissed by that. So vendor locking solution was very lame again. And be mindful, you will find a lot of them in used market because nobody wants them. Stay away from them. Hardware RAID equals no go. So this is how we started. But again, you can find the problem in it. So then new technology came into the market, which we call SAS. SAS is basically serial attached SCSI. Now you have to understand, SCSI was always there. Even in desktop computer, it was this more robust, more kind of infrastructure, basically meant for heavy users. So SCSI was expensive brother of PATA, parallelly attached systems, so to say. And then same way PATA went from parallelly attached technology to serially attached technology, SATA. Same thing happened with SCSI. SCSI was also had a parallel cousin, and then parallel upgraded to serial attached system. Now this debuted, quote unquote, in the market by 3GPS standard at 2004. So these puppies are introduced, and be mindful, because it's made for enterprise, even though hard drive reached its upper limit, meaning we kind of knew by in late 2010, we kind of knew like this will never exceed 250 or 300. Like you can calculate mathematically, like there was an upper limit. You cannot exceed it by too much, like just by that platter. And like, what if the density increased? Again, platter is single point reader. It will not change the speed. We kind of know, like that's why the speed is not growing. We cannot increase the speed unless, like right now, this has one head going from here. You had another head. Like you can do parallel reads on this, but that requires multiple head, and this chassis design is fine-tuned for only one head. Like other companies are trying to have multiple heads that are going like this, basically in one axis, but reading like this. Bit better, but not that much. So we kind of know that there is an upper limit of hard drives. That's why SATA development kind of stopped. SATA development started from 1.5 Gbps. Wow. That basically translates to 100 Mbps. Then SATA 2 happened. That was like 300 megabits per second, 300 megabytes per second. Then SATA 3 happened. That was like, 600 megabytes per second. So SSD level speed. Now be mindful, the hard drive was never that fast, but the interface was. And then people stopped because they realized that was no longer, bottleneck was not the interface, it was the freaking hard drive. So that's why SATA 3 was like, no, that was the last. And by the time we went seriously into basically NAND flash, we kind of realized that SATA interface itself is sloppy. So they created a new infrastructure known as, NVMe, completely different protocol running on completely different pipeline. Pipeline is PCI. But enterprise, they were running whole internet. So they needed something a bit more robust. So SAS. Now SAS kept getting upgrades. Even though it started as SAS 3 Gbps, almost at SATA 2, they kept getting upgraded. Right now, SAS 4 is in the market that has 22.5 Gbps or 2.5 gigabytes per second. That's reaching the speed of these puppy. And that's active in the market. That was debuted in 2017. So anything you are buying right now new generally will come with SAS 4. SAS 5 is supposed to be right now hitting the market, but it's not for some reason. But be mindful, SAS never slowed down. Now, SAS was designed for enterprise, so they had some upgrades. Primary upgrade was voltage was updated, boosted, so to say. So the cable length went from 1 meter of SATA to 10 meters. What does that mean? Like again, 10 meters is not enough for a network connection, but 10 meters is more than enough that you can have a head server that is on top and you can connect a lot of servers. Like you have one head server, a full array of disks, you can connect it, and then full array of disk next to, still connected. Full array here, you can connect it. So 10 meter gives you a lot of length, like lot. That's how outdoor connection, external connection became a thing. Like again, same thing was tried with SATA, with eSATA. eSATA had like bit more higher voltage, bit more oomph, so it could handle a 2 meter length. Well, SAS was like, bro, I got this 10 meters. So that's why you can actually have SAS connection directly going kutu, and then you can plug that puppy. Be mindful, that's higher than Thunderbolt. So 10 meter may sound very little from networking point of view. From any other connection point of view, damn, that's fast, long. So they have that 10 meter. Now that solves one of the problem. How the heck you connect just a bunch of disks to something else? You can, you have the cable length now. Another aspect is supports expander. The protocol itself was built in such a way, it's almost like a data protocol. So how we had back in the old days South Bridge, this system has like a much more deeper integration, and that's why they kept upgrading it. The idea was it was never supposed to be used by one hard drive. That was never the aim. SATA had that sort of aim. It's like one computer, one South Bridge, one SATA drive. This puppy was never designed for this. Was like one controller, hundreds of drives. So they're always pumping up the speed. So the idea is one can easily map hundreds of drive without an issue. So right now the only limiting factor was the silicon. If you had high powerful silicon, the protocol itself, if I'm not mistaken, can support like thousands. Somebody can write down what is the actual limit on one system. It's bonkersly high. It's almost like ZFS. Somebody went all out when they were building it. So the idea was the bus should be fast enough where it can handle multiple drives, not one, multiple. An expander was built in such a way that it can actually smartly allocate. It's like, hey, one user is reading data from hard drive number A, one user is writing data to hard drive number C, another is writing data from all that, and it can allocate that bandwidth. That 2.5 Gbps, it can automatically allocate based on the drive. It's not like, oh, each connection is only limited. It's like, I got this. It can spread out. So your PCI interface will get like 2.5 Gbps. It can do that very effectively. Another aspect is, because again, it was designed from day one to handle multiple hard drives, it supports full duplex. Full duplex is a very critical aspect because again, read and write, how it's done, you can either read or either write. But what if you have multiple drives? You can easily have, hey, somebody is reading data from drive 1, writing data to drive B. What then? The interface, if it's simplex, it will stop, write, But what if read and write, say, that's what it does. So it can easily find one drive, write data to it, one drive, read data from it, same time. So that's fundamental. That's the protocol level. You cannot fake this. It has to be there. Another aspect, it has multipath I/O. Now that's just flexing at this point in time. Multipath I/O is that one drive will have two ports Even though the hardware port will be one, it will have two electrical ports or protocol port, basically like computer wise, and you can have two controllers. Both can work at the same time. Yeah, one drive can work to both. And be mindful, this will scale to hundreds of them. So you can have hundreds of drive, each talking to two. Basically, you can have two controller addressing one disk. So if a controller fries, you have a backup. That's why multi-path I/O was built. No matter what you do, that's why SAS is so freaking expensive. The controllers are bonkersly magical. And that's the industrial part. And then SAS backplane. This backplane development is the reason why we have Netflix and everything. That's the primary reason. SAS was designed in such a way that it can actually handle this sort of backplane expansion. Entirety of internet runs on those back panels. Those back panels are literally the backbone of the internet at this point in time. So if somebody has a Thanos or Infinity Gauntlet is like, there shall not be SAS, yeah, there won't be internet. There's nothing, just poof, nothing. So SAS is very important, and you can understand like 2.5 GPS, and the next one would be even faster. So it's still, even with SSD development, they're like, we good, bro, we good. So what about enterprise, right? So that's the protocol. What about the enterprise? Enterprise is basically characterized by one critical aspect: high availability architecture, meaning they want a lot of nines. There is like simple point, 99% uptime, not good enough for enterprise. Enterprise can generally have 99.9, which you call 3 nines or 6 9, and that could be 99.9999. So 6 nines, or sometimes like for financial sector, it's like 999. That's ludicrously high. So that's the whole point, high availability. Okay, how do you achieve high availability? Everything bare minimum must have dual path. What does dual path mean? Let's say you have power. Where is the power coming from? Generally, wherever you are, you will have one primary provider. Let's say one giant coal power plant, that's the backbone. So let's say you are building an Amazon web server. You will never rely on that only. You will be like, okay, that's one. Let's build another, high voltage line to some other grid section where I can be connected to, let's say, some other hydro dam. Yes, people do that. Yes, that's why people are angry about that data centers are for AI. It's not as cheap. You may think, it's just they are paying money, and they will create their own high voltage line, or at least the contractor will. So it's or state government can also do it. If again, who does that? But it's expensive. So now you'll have two sources of energy. Then it goes to DPU, power distribution unit. PDU. So you will see like in Linux, one would be red, one would be blue. That's the whole idea of it. So one is coming from one channel, another is from another channel. What about UPS and generator? Everything will be duplicated, and generally it may even be from different brand. So you could have Eaton from one side or some other brand from another side to make sure that nothing like oops. So you have one APSC, one Eaton. So likelihood of same failure in both of them is 0. So two DPUs, and then you go to redundant power supply on the main equipment, because so far we are only dealing with AC. What about AC to DC conversion? So you can see like this is the back of those unit. You will have two power supply, and two power supplies are designed in such a way where it's like one can easily guard this, but it will scream. The idea for screaming is that it's in what we call degraded state. One failure, boom, it starts screaming, but hair steel. Nobody who's draining energy from it, basically operating it, they will not notice it, but the physical guy who is in that server room, they will notice it, and they're supposed to replace it very quickly. The reason for that is if another one goes, now it will go downtime. So to make sure that that does not happen, it screams its lungs out. And yes, they have speakers and beepers, and they are loud AF, and they are designed to be loud enough to be 120 decibel. You can hear it like from very far away. They're that loud. So dual redundancy on there. And then we come to SAS. Again, SAS on fundamental level is designed such a way that one PCB can connect it to two controller, and both controller is like, I got this. So if one controller bricks out, it's like, I got this. Second controller is like, I got this. So you have double path per drive, and it has to be wired. You cannot just like, let's cheap out. No, it has to be wired. And dual controllers, you must actually have dual controller, otherwise what's the point? So that again gives you two benefits, either failover or balancing. So that's there. And server itself, now so far we have talked about the hard drive bunches, right? You have JBODs, just a bunch of disk, and everything is just reading the hard drive. Who does the processing? Servers. Now server, nobody is going to put it on one server. That's stupid. That's dumb. Thou shall not do it. So how do we do it? We put in clusters. So clusters are generally nowadays blade PCs, and clusters could be like 8. Yes. On one storage server, it could be as high as 8 computers running on it. So if one computer borks out, it's like, who cares? Like that's how you achieve enterprise level redundancy. And be mindful, the dual path is bare minimum, because be mindful, dual simply means any failure makes you 50% dangerous. Triple redundancy gives you far more oomph. And again, when you are talking about high energy draw appliance like SAS spinning disks, yeah, for that reason, many of them have quad options, power supply option. So one failure only, degrades you to 25%. Because again, one goes, you already lost 50% of capacity. If you have 4, you only lose 25% capacity. You still have enough to like balance it. So for ultra high reliability, like 9 nines, they are like, hey, triple redundancy. Although I'm not sure how will they do the triple redundancy on controller and hard drive, because again, hard drive only has 2 ports. So that's there. Enterprise. This is the primary reason why cloud is so expensive. It's like these things are so expensive, because again, if somebody is paying you, if like let's say I'm paying Google Drive a small amount of money per month, so I can have like, let's say 200 gigabyte in cloud, Google cannot come to me and it's like, oops, I lost your data, I'm gonna sue its ass. So they have to pay this sort of exuberant price to have redundancy, where they cannot just oops it and then have the whole thing duplicated somewhere else, because again, one point of data equals 0 point of data. So that must have 2 data. Now, so far that's cool and all for cloud, but what about yourself? What if you want to do it? Thankfully, our data storage, not thankfully, unpainfully, our data storage has grown. Like we have reached a point where your mobile phone easily consumes 120 gigabytes. So unless you are dumping everything in cloud, and be mindful, any data you're dumping in the cloud that is for free, it's lost. It's already lost. You're gonna lose it one way or the another, or the company is gonna charge money for it. So be very mindful. If anybody's company is like, 100 gigabyte for free, run. You saw how complex JBODs are. Just the JBODs are, not the servers, just the JBODs. They are ludicrously expensive, so nobody can give you it for free. Fundamentally, like it would be a addicting proposition where they're like, hey, 100 gigabyte. Now everybody stores 100 gigabyte. They're like, hey, pay money. It's like, no, I will not. It's like, okay, bye data. And then you're like, wait a minute, I put almost all my life there. Yes, it has happened, has been done. Trust me, thou shall not trust it. So our data needs are reaching a point where a single drive will not be sufficient. Thankfully, even though this was possible always, it has become far more easier. Why? Because free and open source software that is available right now, it has GUI. For example, TrueNAS is a very beloved application at this point in time. Now, it was always there. It's just that it required command line expertise in order to touch it. Now it has a GUI where you will not pull your hair out. So lot of improvement can happen. And there is Unraid also, and Unraid is flexible but does require money, and Unraid is vulnerable to data corruption. And I'm like, if I'm storing data, I better be damn sure the data is actually intact. The reason why TrueNAS can do that is simply because it uses ZFS. Now ZFS were built by people Sun Microsystem, and ZFS is paranoid. It's like hard drive gives it a file, it's like, I don't trust you, man. I do not, sir, I give you the file. It's like, no, I don't trust you. It runs checksum on it. Every file, every block, every transition, it runs a checksum on it. So it's very heavy, and penalty is, you have to build it at one. That's the biggest penalty for a user point of view, home point of view. You cannot just add a hard drive to it. You have to build it at one go. So for common people, it has to be 2 big hard drive. Like let's say 2 8 terabyte hard drive. 8 terabyte hard drives are kind of okay price right now. So you can buy 2 of them and start there. Unraid is unique because it has the ability to, you have 2, then you add another 8. You cannot do that with ZFS. It's very tedious. So TrueNAS does suffer in that regard, but it gives you data trust, basically, so to say. Whereas like, no, if a data is there, I know for a fact it not be bit rotten. And yes, I have gone through enough of hard drive and that I have physically experienced bit rot. So I'm like, I'm not risking my data again. If I'm spending that kind of effort, money and all that, give me TrueNAS. I'm not risking bit rot. So old repurposing of old PC is super easy, and be mindful, we are not in 70s anymore. So old repurpose right now still takes you to like very high performance computer. Heck, my old computer that is like freaking 10, 11 years old, that is AMD Bulldozer FX8350. That can touch 4 gigahertz. So we are not going to like, megahertz. It's like more than good enough, more than high enough. Heck, it has 16 gigabytes of RAM capacity. So I can easily put like 16 terabytes of capacity. You do need 1-to-1 for optimum performance. You can still have offset, but generally it's recommended 1-to-1. And how would you have the capacity? Now be mindful, for majority of people, you do not need to worry about it, because unless you are dealing with some pre-builds, you will have more than 4-6 SATA ports. If you do not have that, if it's a mini PC or something like that, then you have to go into SAS HBA. The reason why SAS, so you can get that external. SAS is compatible with SATA, so you do not have to worry about it. So SAS will allow you to have computer here, hard drive somewhere else, 3D printed enclosure, some other enclosure, whatever have you. That can be done only with SAS. So if you get SATA HBA, it will be internal. So if you want external, you have to go with SAS HBA, host bus adapter. Do not touch anything that claims RAID. If it says RAID, run away. SAS HBA. And software RAID is the path to it. And simple reason why you can do that in 10 years old computer, because computers have matured a lot. And that, again, be mindful, enterprise was stuck. There was a very clear time where from late 2000 to early 2010, they were stuck in an ugly scenario. It's like, dude, we invested millions of dollars in this RAID technology. We have to use it to get our ROI. So they were stuck. But for by the time 2010 rolled around, you could get really good computers like that could do all the parity calculation in the back end without even breaking a sweat. And by the 2020, right now, if you want to build a new computer, you can build with AMD 9000 and you will have such a low power consumption. That's the another benefit of doing modern system rather than an old one. You can do it very low energy, like very low. You can have like 50 watts while running a very high power application, like whole computer 50 watts idle. Only when you are reading and writing on the drives you will consume a lot of power, but you can do a lot in 50 watts. And some people who like spend some time on it, they have systems that go as down as 5 watts idling. So very low, like very good energy efficiency. So PC have matured a lot, and there is a lot of tutorial available in YouTubes and all that, like from forums to companies to everything, it's available. So a little bit of effort. And for anybody who wants to get into IT sector, please do it. Trust me. Like here's the half of IT job is just troubleshooting. You would think, oh, I'm gonna do things. Nah, half of the time you're just gonna do troubleshooting. Another half you're gonna do troubleshooting. Trust me. It's one of those things that's the moment I have all the programmer friends who have worked in big things and all that, they always start, oh, we are doing this. As they get, yeah, I'm fixing it. Just abracadabra and let's make sure it works. So trust me. And this sort of things will teach you exponentially. Like Kubernetes, do it on hardware. Docker, do it on freaking on hardware. You will learn how to do troubleshooting, and the troubleshooting equals more money. So do it yourself is a really good pathway to take. If my brother donates me 2 hard drives, I'll do it. So this was my presentation on just a bunch of disks. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show my disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free. And as always, thanks for watching.